learn how to actually round numbers in calculations from numbers that came from measurement devices. All numbers come from measurement devices, and in our labs and in our activities in physical science, we like to measure and then crunch the numbers to solve for things. That could be a density, that could be a sum, a product, an area. But when we measure to come up with an area or a volume, we have to follow some important rules in controlling the amount of error that exists or built in a measurement. Let's start this way. We take a measurement, and I'll just write the word measurement. And that could, of course, come from a ruler, a triple beam balance, a thermometer. We know there are, from the measurement, errors. In these errors, now, of course, before I talk about the error, of course, comes from a level of uncertainty. And that comes from the guess in the measurement. As you have already learned, a measurement are all numbers on the measurement device plus the guess in between, let's say, the last two calibrated values. We guess. Now, of course, some measurement equipment is more expensive and more precise than others, and the guess is in the smaller region. But no matter what measurement we use, we always come down to at least one guess. And therefore, because of that, there is inherently some errors involved in measurement. Now, when we take these numbers from measurement and we look to make something, let's say, of an area. Okay, an area we know is a length times a width. If we're going to calculate it with a length, right, take centimeters of some sort and times it by another centimeter value, you should know that we should be getting a centimeter squared. That's a unit. Centimeters times centimeters is centimeter squared. But what I'm after here is that when you get your number, we're going to have to round to control for the error. What I mean by that is, think about some number that's a length built from some measurement device that has a guess in it. You're timesing it by a width that came from measurement that also has a guess in it. So your number is going to have some part of it that does not reflect the true value because you have multiplied a guess times a guess. Yeah, there's some numbers you're certain of, but you have some numbers you're uncertain of, which means we're going to have to lose them and round them off. So what we're going to do is we're going to control for the compounding or the adding or the subtracting of error that comes from the measurement device, and all measurements have it, by rounding our answers in calculations with numbers that have significant digits or measurements. We round off a certain way to limit the amount of error in our overall result. Let me explain. Let's start off with numbers that we add or subtract, okay? And let's start with a very simple explanation or example. So let's take 1.1, 1.11, and then 1.111. These are all centimeters. Let's give it a unit. A number without a unit makes no sense. Get in the habit of that. And let's just say we're looking for the sum. For whatever reason, we're summing these things. All right, these measurements. Okay, so let's come up with a raw number. These are the numbers that show up in your calculator that you've been writing down in your math class. Now, when I add these together, I get 3.321 centimeters. Okay, now, what does this mean? Is this something that I'm going to write? Okay, in my answer, and the answer would be definitely not. Okay, if I was to look carefully at this, all right, let's see, let's get green. Look carefully. This number, this first question had precision out to the tenths place. I don't know where the green went. And then I had precision for the second one out to the hundredths place, and then the third one had precision out to the thousandths place. What I'm saying to you, party people, is that This measurement here is the strongest, gives me the most, is the weakest, because its guess, and that's where the black line is, its guess is in a larger part of the number. So here's the guess. The last number in a significant figure or a measurement, same thing, is the guess. So this is the weakest number. Why is it the weakest number? It gives me the least amount of information. Why? Because it has a larger error. This error is in the tens place. This error is in the hundreds place, and this error is in the thousands place. So the strongest number, the number that's more precise, right? That's giving me a lot more precision. Okay, this is the strongest number, or the most precise number. Now, I'm going to add a very precise number with two other numbers that are not as precise. So what I'm saying is our answer, 3.321, is reflecting, if we keep it that way, the most precise device. But when you think about it for a second, where is the weakest link? If you've got a team, you're as strong as your weakest link. And my weakest link on this team are these two numbers, because their errors, okay, are bigger. The guess is in a bigger part of the number than this guess. This guess is in the thousands place. So these two numbers are the weakest link. I cannot reflect an answer that's greater in precision than the other numbers that are weaker. If I was to write this number as is, I am overcompensating for the precision that doesn't really exist. Am I really this precise to the thousands place? Do these numbers really have meaning if I'm adding them to other numbers that are weaker? What I'm saying is there is a weakness in this number that has a lot of uncertainty because I added numbers with greater error. Yes. So what I'm going to do is take this and I'm going to round it. And I'm going to round it so that my number reflects the least precise measurement that was used to come up with this answer. I can't overestimate the precision like here. So what I'm going to do is I'm going to round to the least number of decimal places. I know I've got a lot written here, as I normally do, but notice this has 1 decimal place. This has 2 decimal places. This one has 1, 2, 3. So the least number of decimal places is my weakest number, and I'm going to round to that space. So I'm going to round to the tenths place. That is the lowest number of decimal places. So I round this number to the tenths place, which represents my weakest number. And I get 3 point. Now, if I'm going to round to this number, I've got to look at the next number. If it's above 5, it makes the 3 go to a 4. Since this 2 is less than 5, it goes 3.3 centimeters. Let's make that better. So I'm going to round this number into 3.3 centimeters. What did I do with the rest of this number? I got rid of it because it doesn't mean anything, because it was made poor by adding a weak number with a lot of misinformation. This is a lot of guessing in here in the 10th. So we round our numbers when we add or subtract by using the precision rule, and we round by the weakest link. We can't report an answer that is stronger than the weakest number that was used to make the answer. Again, I can't use 3.321 here and just keep that in my calculator, because these numbers aren't that strong. They're made from errors. I've added errors together. So I have to round and get rid of these numbers that really have no meaning because they were just made by adding errors. More importantly, my answer reflects the weakest, most imprecise result. and therefore my number reflects the weakest number in terms of precision. So when you report a number in calculations, when you add or subtract, you round off to the least number of decimal places. That's the precision rule. And I can give you the rule, but understand you're reporting a number that reflects the precision of the weakest device that makes all the numbers, good devices, go bad. We're as strong as our weakest number, okay? And that's how that works. So when you add or subtract, you count the number of decimal places. In this case, there was 1, this was 2, and this was 3, and you round off just to 1 decimal place, getting rid of these numbers that really have no meaning because they were made from what? Adding errors onto each other. It's the precision rule because we're rounding off to the least precise number. And you should know as you add more decimal places, your numbers get more precise. Okay, now that's when you add or subtract. What if you multiply? Now you should understand when you multiply, what you're doing is you're adding several times over and over and over again. So when you multiply, you probably would expect, how do we control for this error? We should round off to the least number of decimal places. Well, the answer is no, we don't do that, because when you multiply numbers together, you will wound up changing the actual value of your number. So let's say we're going to multiply 315 to 20 point. Let's say we're going to find an area. This could be an area. This could be centimeters, and these are both centimeters. And we multiply centimeters by centimeters, we get centimeters squared. Okay, take your calculator, and here we go. We're going to take 315, and we're going to times it by 20. Okay, so I get 6,300. Of course, not a great number, but we'll take it. Now, the question is, does this number reflect the actual value of the significant figures? Well, just by luck it does. All right, so it's not a great example, but let me explain it. What's happening here is this is my error. This error is in the tens place, and just like the other one, this error is in the tens place. So the precision is the same, but I'm multiplying this guess times this guess. In fact, I'm timesing this measurement's guess. I'm multiplying it 315 times. I'm adding 20 315 times. That's what multiplication is. So 20 added to each other 315 times is going to give me this result. All right? So I'm adding the error built in this measurement 315 times. Now, if you add the error into the measurement that many times, don't you think you're going to change the actual value of the number? And the answer is yes. The actual value, the known value, is the accuracy rule. So what we do is we round so that we have not just precision or decimal places, but the number of sig figs. Let me explain. So because we're multiplying, because we're adding many times over, what we do is we look at the number of significant digits. Why? Because the significant digits will maintain our value. If we allow the error in this measurement to be compounded 315 times, it'll change our answer. So when we multiply and divide, we round by the least number of significant figures. How many sig figs in this measurement? Well, that's 3. How many in this measurement? Okay, well, there's 2 with the point there. Let me change the problem a little bit. Let's pretend that this point isn't there. Let's pretend that was 20. Okay, now if that's a 20 without a point, we should all know that that has how many sig figs? That's correct, 1. Right? No decimal point, this is just a placeholder. So I'm going to multiply a number with 3 significant figures. That means 3 numbers came from a measurement. I'm going to times it by a number where only 1 number came from the measurement, which was a guess. And you can see that the guess in this case, for this measurement would be here. This didn't come from the measurement device, it's a placeholder. Here's a guess here. I'm going to take a guess that's in the tens place, and multiply it what? 315 times. Can I be exactly certain that this is the number? Of course not. To control for the value of my number, I'm going to round off to the least number of sig figs. This one has 3, a lot of information. This one only has 1, not a lot of information. So I've got to round my number, this is the raw number that I get my calculator, to one significant figure. Sig fig. That should be sig. Okay, I can do it. Sig fig. All right, so this becomes 1 sig fig. Now, we're rounding to a decimal place, so I'll round it to a sig fig. So 6,300 has 2 sig figs. So I got to go from out in, so I got to go 6. Look at my next number, 3. It's less than 5, so it stays. So this becomes 6,000. Weird. I get rid of the 300. Centimeters squared, and that's how I round. I didn't round by decimal places. I round by the least number of sig figs. Notice something. I got rid of 300. Why? Because I was not sure of it. Why wasn't I not sure of it? Because I was multiplying the error in this weak link. This has 1 sig fig. These guys have 3. I round off my answer to the weakest value that made the computation or the calculation. My weakest link is the 20. It only has 1 number that came from a measurement device. Therefore, my final answer should only have 1 number. I keep the 6. I can't make this 300. I go from out in. So 6,300 rounds off to 6,000. If this was 65 or 66, I'd round to 7. And in this way, it tells me that, hey, I am certain of what? Of exactly this 6. The other numbers I'm not. So if I was to order some steel for a bridge, and I had 315 times 20 for some reason, and it gave me 6,300 tons, I would say that I need about 6,000 tons. I'm certain of the 6,000. If I said I need 6,300 tons, I'm not certain of that because I'm what? Multiplying the error. So to control for the error, when you multiply, you round off to the least number of sig figs to maintain your number. When you add or subtract, you round off least number of decimal places to maintain the what? The weakest precision. Now, accuracy, we also what? When we multiply or divide, I didn't say that. When you divide, you're subtracting a number of times. So you're doing that over and over and over again. So that to maintain your what? Value of your number, you round off to the least number of sig figs. When you add or subtract 1 or 2 operations, you don't change your number with the error, but you could change the precision. All right, so least number or the least precise device for adding and subtracting, the least significant number when you multiply or divide. Let's go to your homework and let me show you this in action. Okay, so here we are with the significant ditter worksheet. That's part of your homework. And let's go through some of these. Let's take your calculator. Let's make this bigger. And let's look at A. Oops, that's too big. Okay, let's look at A. And let's add these together. So I take my calculator, just plug it in like you know it's 16.5. And now, of course, this represents probably centimeters or something. I left the units off to keep this simple. Plus 8 plus 4.37. Okay. The raw number I get is 28.87. Okay, and of course some units, so I'll just write unit. However, don't put that as your answer. Why not? Well, when you add or subtract, you round off to the least precise number. Precision is based on where that guess is. This guess is in the hundreds place. This guess is in the single digits. This is the tens place. The weakest link or the least precise device is right here. The error is too big here. So I cannot have an answer that's more precise than my weakest link. So I have to round off to the single digits place right here. So I look at the next number, 8. It's above 5. So this rounds off to 29 units. And that's the answer. Notice the 9 is in the single integer space, which it reflects the what? The least precise device. Okay, try letter B right now and pause me. So when I add 13.25 plus 10 plus 9.6, again, they could be centimeters, I get a raw number of 32.85 units. That cannot be correct because you're more precise than your what? Least precise number, which in this case would be in the tenths place. So I have to round to the tenths place. That's the least number of decimal places. This has 1, 2. This has 1, 2. This has 1. So I got to round it off right here. So I look at my next number, 5. 5 or greater makes this become 30. This 2 becomes a 3 because the next, I'm sorry, bad. We're rounding off to 1 decimal place. I do make mistakes. I am tall. So 32 stands. We're going to round off to the least number of decimal places, which is the 10th. So this 8 becomes a 9 because this 5 is greater. This 5 is 5 or greater, so you go to the next number. And of course, it's a unit as well. So pretty simple stuff. If you subtract, like letter F, 23.27 minus 12.058, you get a raw number. Let's move this over. Where am I? Okay, so let's get the raw number here, 11.212. It's some kind of unit, right? But I round off to 1, 2, 1, 2, 3. The least precise number is here. So I'm going to round off to 2 decimal places. I look at this next number, 2. It's less than 5, so it stays. The answer is 11.21, whatever unit we're using. Okay, so you're rounding so that in the addition and subtraction, we're maintaining our precision. We're as precise, 10th place, by the least precise device that was used to get that number for the calculation. Now, when you multiply or divide, let's go down to these guys. Remember, division is really subtracting a bunch of times, and multiplication is adding a bunch of times. If you're going to add the errors in these measurements over and over and over again, you're going to change your answer. You're going to change the accuracy of your answer. So we're not going to round off by decimal places. We're going to round off by significant figures, how many numbers exist. So look at A. Let's put in our calculator, 2.6 times 3.78. And I get 9.828 units. Okay, we're not looking at decimal places. This has 2 significant digits. This has 3. This has more information. It's a better piece of equipment. It's giving me more numbers. This is a weak link. So we're going to round off and try to control the compounding of error when you multiply, which is really adding the error a bunch of times. So to control for that, we're going to round off to 3 not decimal places, but 3 significant figures. So I'm going to round off here. This 8 is bigger or equal to 5, right? So it makes the next number get bigger. So 9.83 is how we round off to maintain the accuracy of our number. Okay? If you did a division problem like H, 35 divided by 0.62 gives you a huge number. I'm going to write it up here. 56.4516129. Could all those numbers mean something? Of course not. This only has 2 significant units. This one only has 2 significant units. How can I take 2 meaningful numbers and 2 meaningful numbers here, do a calculation, and give you what? All 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 meaningful numbers. I can't do it. I can only be what? Certain of just 2 numbers. So I round to what? I round to 2 significant figures. I look at the next one. It's 5 or greater. In this case, it's below 5. So I stop at 56. These numbers are meaningless. I'm not certain of them. I'm certain of about 56 using these two numbers. My number cannot be more, my reflected answer in a calculation can't show more information than the weak links used to get it. These only have two pieces of information, so I should only have two left. That should make some sense to you. Of course, this is a unit. All right. Now, I'm asking you to do, I think, A through D for both of these. And I would like to go to another old ditto for a second. So hold on. This is a worksheet that we did already, but I want to talk about how we round. Okay? Let's look at number 3. We start with 270 pounds. Oops. How many significant figures are there in 270? Yes, you are right. There's only 2. There's no decimal place. So I've got a number with 2 significant digits. I'm going to times it by a converting factor. Converting factors we did not measure, so they don't go into the rounding. So I start with 2 significant digits. Guess what? I should end. How can my answer have more information than the 2 that I started with? Again, these converting factors do not come into play because we did not measure them. So if I start with 2 sig figs, my answer should have 2 sig figs. So I have to round this to 2 sig figs. So I need the first 2, and the rest I'm going to lose. I look at the 2 here. The next number is less than 5, so my answer becomes 120 kilograms. Notice I didn't put a point there. I don't put a point there because I want 2 significant numbers, not 3. See that? My answer reflects 2 significant digits. I started with 2, I get back out 2. Okay? These numbers aren't playing here. If you go on to another one, let's go on to number 5. Number 5, I have 25.6. How many significant units am I starting with? Of course, all 3. I times it by converting factors that I did not measure. I did not measure at all, so these don't come into play, so I should get back out 3. And I round this to 3 significant units. I look at the next one behind it. It's a 1. It's less than 5, so this is 12.1 liters. My answer reflects the information I started with. I can't have more information than the measurement device used to get it. So we round that way. So when you do conversions tomorrow, whatever significance you start with, you should have at the end. Notice this is multiplying and dividing, so therefore I'm following the accuracy rule. Okay. Please finish the questions I have posted on the website.